extensions, NashProp, and beyond. At this point, it is of course natural to ask what can be done when the underlying graph of a graphical game is not a tree. Remaining close to the development so far, it is possible to give an heuristic generalization of algorithm approximate tree dash to the setting in which the graph G is arbitrary. This algorithm is known as NashProp, which we will now briefly sketch. By heuristic, we mean that the algorithm is well defined and will terminate on any graphical game, but unlike approximate tree Nash, the running time is not guaranteed to be polynomial in the size of the input graphical game. In general, we should expect provably efficient algorithms for equilibrium computation to require some topological restriction. Since allow G to be the complete graph reduces to the classical normal form representation. Recall that the main computation at vertex V in approximate tree Nash was the computation of the downstream table T of WV from the upstream tables T of V UI. This assumed an underlying orientation to the tree that allowed V to know which of its neighbors were in the direction of the leaves identified as UI, and which single neighbor was in the direction of the root identified as W. The easiest way to describe NashProp informally is to say that each V does this computation once for each of its neighbors, each time pretending that this neighbor plays the role of the downstream neighbor W in approximate tree Nash, and the remaining neighbors play the roles of the upstream UI. If all discretized table entries are initialized to the value of 1, it is easy to show that the only possible effect of these local computations is to change table values from 1 to 0, which in effect refutes conditional NE assertions when they violate best response conditions. In other words, the tables will all converge, and in fact, in time polynomial in the size of the graphical game. However, unlike an approximate tree Nash, the tables do not represent the set of all approximate NE, but a superset. This necessitates a second phase to the algorithm that employs more traditional search heuristics in order to find a true equilibrium, and it is this second phase that may be computationally expensive. One of the merits of NashProp is that the first table computation phase can be viewed as an instance of constraint satisfaction programming (CSP), which in turn plays an important role in many algorithms for probabilistic inferences in Bayesian networks, Markov networks, and related models. The NashProp algorithm was also inspired by and bears a fair similarity to the well-known belief propagation algorithm for Bayesian network inference. We shall see other connections to these models arise in our examination for correlated equilibria in graphical games, which we turn to now.